Alright, so the very last problem that we're going to work on today is about an airplane, and it is speeding up. It can be modeled by the equation 7.230 square roots of t, and we're going to talk about velocity, and we're also going to talk about time. So we are going to make our variable box off to the side where v is velocity. They say velocity happens in meters per second, so I'm going to write MPS over here, meters per second, and we're going to write t, which is time in seconds. They're going to list that down here for us, so we already know that that's what this part is. Okay. So the first thing I'm going to do, they asked me for the plane's velocity at 6 seconds. So in part A here, they gave me 6 seconds, and what I need to do is substitute it into this equation and see what I get. So I'm going to graph it first, 7.230, and then there's going to be a square root of x. Hit enter, and you're going to see your function pop up. I can't really see what's going on here, so I'm going to go and change my window. I can go into window settings and try to manually type in window function, which is fine. I can just put in domain and range there. The other thing I can do is go down to the very bottom zoom fit and have it estimate a curve for me so I can see a little bit better. So that's what I'm looking at. This is my plane velocity in meters per second over time. Velocity over time. So we can see that as time goes on, the velocity increases, and it's still increasing, but it kind of like tapers, you know? It's not as steep anymore. And that makes sense because at a certain point you're going to get fast enough that you don't need to go any faster. So, what is a plane velocity at 6 seconds? To do that, we can just go to a table, Control T, and we go down to 6 seconds. At 6 seconds, velocity is 17.710. So we can write in for part A 17.170, and that's in meters per second. So 6 seconds, 17.170. So at 6 seconds, velocity is 17.170 meters per second. Now, in part B, when does the plane's velocity reach 90 meters per second? In part B, when does the velocity reach 90 meters per second? So, at what time will velocity be 90? So, in our equation, velocity is 7.230 square roots of t. We're going to substitute in on the v side. 90 equals 7.230 square root of t. Divide that by 7.230, and you get that 90 divided by 7.230 is going to give you 12.448. So 12.448 equals the square root of t. That'll cancel, so we just have the square root of t on that side. To get rid of this radical, we'll want to square both sides, right? So that cancels, and you're left with t equals whatever 12.448 squared is. So we'll square 12.448, and we get 154.956. 154.956. We'll write that in over here. 154.956. So at 154.956 seconds, velocity is 90 meters per second. Good deal. Now let's graph the function on the coordinate plane. First thing the graph needs here is a title: Airplane Velocity. This is a good one. They've named velocity and time for the seconds. So let's see about getting our coordinate points here. Alright, I'm going to go back to my document here that I've been working on, and I am going to take this table off so I can get a better picture. My window settings should be what I see on the x-axis, so from 0 to 65, and then on the y-axis from 0 to 70. Go to Menu and Window Zoom. The very first option is Window Settings. So the minimum should be 0, the maximum should be 65 on X, and then on Y we'll go from 0 all the way up to 70, and everything else can just stay the same. At this point, we're going to hit OK, and now we have a better view. This is what our graph should look like when we're all done. So now I can go back to the table, and I'm going to get some coordinate points that are whole numbers. A good one to start with is 0, 0. Let's scroll down and see if we can find some more whole numbers, or some numbers that are really close. This is pretty good. 11 and 23.9, or 12 and 25. Those are all pretty close. So we can say 11 and 24, that's really close. So we'll go to 11, go up to 24. It's a good one. 15 and 28 is another good one. Okay, keep on going. So 30, 39.6. Right there, almost 40. We'll go down. Let's try 45 now. 45 is matching with 48.5. We'll go down a little bit further now to 60. 60 happens at 56. So we're going to go to 60, 56. 0.003, and then we can go up to maybe 65, which is our last available coordinate point on this graph, and it's going to be 58.2. So almost to 60 here at 65. And there's our full graph. So let's go ahead and be very smooth when we connect the dots. Okay. Go back in, smooth out my curve. And I'm going to have my curve end, hard stop right here at 65. It's going to ask me if the plane speeds up for 20 seconds, what would the domain and range of the function be? So if the plane speeds up for 20 seconds, we're talking about from 0, 0, right, all the way to 20 seconds. So they just want us to focus on this piece right here. And we're going to look at the domain and range. Alright, so the domain is right here. That's pretty straightforward on the x-axis. The domain goes from 0 to 20. Now, what is the range? Well, we know that the coordinate point 0, 0 happens, so that's for sure. But I don't know what's going on when x is 20. So I'm going to come over here and figure out when x is 20, what will y be? And when x is 20, y is 32.334 meters per second. So there's my domain and range, and you can write it in this notation. We are more familiar with this notation, and you could also try this notation for the range. Part E, how would you graph the function? F of t, how can it be transformed? So, the typical square root function looks like this. And we're trying to figure out what kind of transformation happened to create this? So what does a number coefficient in front of my grouping do? Well, because it doesn't affect, it's not having the effect here on the inside of the grouping, it's having the effect on the outside. In other words, it's not going to affect the independent, it should affect the dependent variable. So this is going to be a vertical stretch. Of 7.230. So that's how the graph would be transformed. Alright, let me know what questions you have in the comment section, and I'll get right back with you. Take it there.